Hello, this is Dr. Brown. In this video we're going to look at improper integrals, and let's get on with it. In this slide we have a couple of functions here. One is function of x equal ln of x over x squared, and we will be asking the question, does the integral from 1 to infinity of f of x dx equal a finite number? Now, of course, you can imagine trying to integrate as far as you can to the right and letting x approach infinity. To some it might seem that the amount of area there, since the length would go to infinity, that the area would go to infinity. But as we will see in some cases, the function of x approaches 0 as x approaches infinity, and it approaches 0 so quickly that the actual area is a finite number. Although it does turn out as f of x, if f of x approaches 0, it does not guarantee that the area will be a finite number. Now, the other function here is f of x equal 1 over the square root of x, and notice it has a vertical asymptote. At x equals 0. And so you might wonder, is there a finite value for the integral from 0 to 1 of 1 over the square root of x dx? And we will be exploring these questions as we develop this video. First, let's look at a fairly simple function that you're very familiar with, the exponential function that is decaying. In other words, it's e to the minus x over 2. And what we're going to try to do here is try to calculate the integral from 0 to infinity of e to the minus x over 2 dx. Well, the question that arises is, how would you go about doing it? Something that you probably might think of is calculating the limit as b approaches infinity of the integral from 0 to b e to the minus x over 2 dx. So you would calculate the integral from 0 to b and then see what happens as b approaches infinity. Well, you can see that this equals the limit as b approaches infinity. The antiderivative of e to the minus x over 2 is minus 2e to the minus x over 2, and we would evaluate it at 0 and b, and you can quickly see that this is minus 2e to the minus b over 2 plus 2, and let's write this as a limit as b approaches infinity. And you can quickly see that this will approach 0, because you can rewrite this as minus 2 over e to the b over 2, and as b over 2 goes to infinity, this has to equal 0. So we do get a finite number of 2. So the area under this curve as the limit, the right-hand limit approaches infinity, is equal to 2. Now, here's how we're going to try to calculate limits or calculate integrals like this that we call improper integrals. We're going to call them improper integrals of type 1. If we have a function f of x that's continuous from a to infinity, we're going to try to calculate the limit of the integral from a to b as b approaches infinity of f of x dx. Now that's if the function goes from some value of a out to infinity. Now the function also could extend from minus infinity to some value of b, and so you could imagine calculating the limit as a approaches minus infinity of a to b f of x dx. Now you might have a function that its domain is all real numbers, and the domain would be minus infinity to plus infinity with the function extending all the way to the left and all the way to the right. So in this case, we would break the function of x into two pieces, and maybe some number c, and then calculate the integral from minus infinity to c, and then add the integral from c to infinity. And if you looked at both of these integrals, if they both converge, the entire integral is said to converge. So we're going to start talking about whether an integral converges and thus has a finite amount of area under it. And if it doesn't, the improper integral diverges and the area would approach infinity. Now let's return to one of the functions we looked at earlier, and we're going to try to calculate the integral from 1 to infinity. So we want to go 1 to infinity of ln of x divided by x squared dx, and we're going to take the limit as b approaches infinity of the integral from 1 to b of ln of x over x squared dx. So you look at this and say, how are we going to calculate this integral? You can't look at it and say, oh, I know what the antiderivative is. Turns out that this particular integral can be solved using partial fractions. So let's write down the partial fraction formula, which says that the integral of u dv equals uv minus the integral of v du. So we're going to use this as we pick our u and our dv. So let's pick u equal ln of x, and du, of course, would be 1 over x dx. And if we pick dv is equal to 1 over x squared dx, then its antiderivative would be v equal minus 1 over x. So now we can write that the integral from 1 to b of ln of x x squared dx is equal to uv, which is minus ln of x over x, and we want to evaluate it at 1, and b, minus the integral from 1 to b of minus 1 over x squared dx. That is minus the integral of v du. So v du would be minus 1 over x squared dx. So now we can see that this is equal to minus ln of b over b plus ln of 1 over 1. Of course, that's going to be 0. ln of 1 is 0. Plus the integral, minus times the minus plus, obviously, the integral from 1 to b of 1 over x squared dx. So this is going to equal minus ln of b over b. The antiderivative of 1 over x squared would be minus 1 over x, and we'll evaluate that between 1 and b. So this whole thing equals minus ln of b over b minus 1 over b plus 1. Now, we can say now that the integral from 1 to infinity of ln of x over x squared dx equals the limit as b approaches infinity of minus ln of b over b minus 1 over b plus 1. Now, obviously, minus 1 over b approaches 0, and using L'Hopital's rule, we can show that minus ln of b over b as b approaches infinity also goes to 0, because you remember that the limit of minus ln of b over b as b approaches infinity. Both numerator and denominator are approaching infinity, so we apply L'Hopital's rule and take the derivative of the numerator, which is minus 1 over b, the derivative of the denominator, which is 1, and take the limit of that as b approaches infinity, and that is 0. So now we have that the integral from 1 to infinity of ln of x over x squared dx is a convergent improper integral whose value is 1. On the next slide, we have another improper integral that extends from minus infinity to plus infinity. We're going to take a shortcut here. Instead of breaking it up into two pieces, we're going to note that this is a even function, and if either side of this integral is convergent, it will equal 2 times the integral from 0 to infinity of 1 over 1 plus x squared dx. And so we would want to calculate the limit as b approaches infinity of 2 2 times the integral from 0 to b of 1 over 1 plus x squared dx. That would equal the limit as b approaches infinity of 2 times inverse tangent of x as you go from 0 to b, which is the limit as b approaches infinity of 2 inverse tangent of b minus 2 inverse tangent of 0. This, of course, is 0. And the inverse tangent of b as b goes to infinity is going to be pi over 2. You probably recall that tangent of pi over 2 is not defined, as you graph the tangent function, it's a vertical asymptote at pi over 2, but inverse tangent of b as b goes to infinity is indeed pi over 2. So this improper integral will have a value of pi. Now, we're going to look at an improper integral from 1 to infinity of 1 over x to the p dx. And we're first going to look at p equal to 1, and I think we've looked at this before. The integral from 1 to infinity of 1 over x dx equals the limit as b approaches infinity of the integral from 1 to b of 1 over x dx, and that equals the limit as b approaches infinity of ln of x from 1 to b, and that equals the limit as b approaches infinity of ln of b minus ln of 1. ln of 1, of course, is 0. ln of b as b approaches infinity is infinity, so it diverges for p equal to 1. Now, let's look for the case where p is not equal to 1 and calculate the integral from 1 to b of 1 over x to the p dx, which is equal to integral from 1 to b of x to the minus p dx, and this equals x to the minus p plus 1 over minus p plus 1, and going from 1 to b. So this equals b to the minus p plus 1 over minus p plus 1 minus 1 to the minus p plus 1 over minus p plus 1, and this is equal to b to the minus p plus 1 over minus p plus 1 plus 1 over p minus 1. Now, let's look and see what the limit of b to the minus p plus 1 over minus p plus 1 plus 1 over p minus 1 is as b goes to infinity. Now, if p is less than 1, note that b to the 1 minus p, which is this term, goes to infinity, because if p is less than 1, that's b to a positive exponent, and as b goes to infinity, it goes to infinity. If p is more than 1, note that b to the 1 minus p goes to 0 as b goes to infinity, and therefore it converges. So we have that the integral of 1 to infinity 1 over x to the p dx equals 1 over p minus 1 for p more than 1, and it diverges or equals infinity for p less than or equal to 1. And this will be an integral that we'll be using to evaluate or judge as to whether or not other improper integrals converge or diverge. Now let's look at another kind of improper integral. That's where we have a vertical asymptote. This will be a good bit easier to calculate. We want to know if the integral from 0 to 1 of 1 over the square root of x dx equals a finite value. Does it converge? To do that, we're going to take the limit as a approaches 0 from the right of the integral from a to 1 of 1 over the square root of x dx. And this can be written as the limit as a approaches 0 from the right of the integral from a to 1 of x to the minus 1/2, and this is equal to the limit as a approaches 0 from the right. The antiderivative of x to the minus 1/2 is 2 square roots of x. We evaluate it at a and 1, and this equals the limit as a approaches 0 from the right of 2 minus 2 square roots of a. Well, as a approaches 0, this approaches 0, so the integral has a value of 2. Now let's look at another improper integral in which it has a vertical asymptote at x equal 1. Um, Here we want to look as B approaches 1 from the left. So let's take the limit as B approaches 1 from the left of the integral from 0 to B of 1 over 1 minus x dx. The antiderivative is going to be minus ln of 1 minus x. And we want to take the limit as B approaches 1 from the left. We want to go from 0 to B. And so this finally equals the limit as B approaches 1 from the left of minus ln of 1 minus B. Minus ln of 1. Of course, ln of 1 is 0. As B approaches 1 from the left, this approaches minus infinity, which is plus infinity. So the integral diverges. And there is one last integral in which we see a vertical asymptote, both going to infinity at x equal 1. And we want to first look at going from 0 to 1 of 1 over x minus 1 to the 2/3 power dx plus the integral from 1 to 3 of 1 over x minus 1 to the 2/3 power dx. And let's on the first go here, do the very first one. And we want to look at the limit as B approaches 1 from the left. We're going to do this side of the integral from 0 to B of 1 over x minus 1 to the 2/3 power dx. And this equals the limit as B approaches 1 from the left. The antiderivative of this, as you can see, is going to be the antiderivative of x minus 1 to the minus 2/3. So power plus 1 over power plus 1 is going to be 3 times x minus 1 to the 1/3 power from 0 to B. And this is equal to the limit as B approaches 1 from the left of 3, plug in B minus 1 to the 1/3 power minus 3 minus 1 to the 1/3 power. And you can see that this will go to 0, and we'll be left with minus minus 3 times minus 1 to the 1/3 is minus 1, and we get 3. So this side is going to be 3. And now let's go to the other page and do the limit as C approaches 1 from the right of the integral from C to 3 of 1 over x minus 1 to the 2/3 power dx. And this equals the limit. C approaches 1 from the left. The antiderivative is 3x minus 1 to the 1/3 power. We want to go from C to 3. And we get the limit. C approaches 1 of 3 times 2 to the 1/3, plugging in 3, minus 3 times C minus 1 to the 1/3. As C approaches 1 from the right, this goes to 0, and we get that the integral is 3 times the cube root of 2. So the entire integral from 0 to 3 of 1 over x minus 1 to the 2/3 power dx will equal 3, which is the first part of the integral, plus 3 times the cube root of 2. So that is part 1 on improper integrals, and we'll go now and make one more video.